In this video, I'm going to describe how to splice two spectra together from two different spectrometers in Specpr. This is called a merge. A reason we'd want to do this is to create one more complete, longer spectral range spectrum for use in comparison with other data, for example, spacecraft instrument data. One of the things that we need to do if we're going to compare to other instruments is we need the reflectance data, we need the wavelengths, and we need the band passes for both spectrometers to merge into the synthetic output spectrum or combined output spectrum. Okay, we're using the same setup directory as in previous examples, tutorials, and we'll look at the R1 file. I want to get some spectra from this Specpr file. And in particular, I've chosen for this example, we're going to look for forsterite. And in particular, there are two different forsterites we can see here, SC and globe. We're going to use the SC. SC is San Carlos, so this is a San Carlos olivine. We have a 2151 spectra, that's an ASD spectrometer covering 0.3 to 2.5 microns, and 2048 channels is ultraviolet covering about 0.2 to about 0.9 microns. So we need to combine these. There's generous overlap, so we'll need to choose the overlap region. So the first thing to do is start Specpr. Remember my alias, which runs this command. So we need the wavelengths and the resolution. The wavelengths, and we have no pointer to the resolution for the ocean optics data. We'll need to synthesize that, or if you have that measured from your spectrometer and have it in another place, you need to go find it and add it. But it's not here, and I've searched through this file and it doesn't exist in this file that I found anyway. So we need 6. So SPS 0008 is assigned to Y, so Y6, copy to U. Y12, the resolution, bandpasses, copy to U. You don't need spaces here. Then the reflectance spectrum for the ASD, Y to U. Then next we do the ocean optics spectrum, so Y1811 to U. And since we don't have this, the next step is we'll synthesize the band passes for the ocean optics and then copy the forsterite over. So we do that, it's going to be quick, done. And if we do a so here we see the ASD wavelengths, wavelengths and band passes, the forsterite spectrum, and the wavelengths to the ocean optics. So the next thing we need to do is get the band passes for the ocean optics. So let's go to math, and we'll use a special function called the line segment generator, and we'll do line, have to spell correctly. And that's one of the special functions, F1 through F whatever. Right now we have those wavelengths, so we need to set the wavelengths to be U45. Okay, so you see the wavelengths were set correctly. This is a reminder. You need to manage which wavelength set you're going to use. And there's a reason for this. While it puts a burden on the user, it allows you to explore different things. For example, you could have, for one spectrum, you could have wavelengths in microns, wavelengths in nanometers, wavelengths in wave numbers, or wave numbers, not wavelengths. So, and then you could plot your data with any one of those, so you can freely point to whichever one you want to use. But it's up to you to manage which one you're going to use. So always check that you're using the right wavelengths when you're working with multiple spectra. If we set the wavelength pointers, then there's an easier way to manage those. Okay, so this is fine. So channel 1, so the band passes are of the ocean optic spectrometer are approximately 1.5 nanometers, but our wavelengths are in microns, so it's 0.0015. Then channel 2048 is 0.0015. We're done. Write the results to U. And this should be and that's probably good enough. And we see the numbers are very low. Well, let's okay. Let's change our wavelength range for the whole data set is going to be 0.2 to 2.5. Oops, W 0.2 to 2.5. Okay, so you see the ocean optics data goes out to almost 0.9 microns. Let's change our scale 0 to 1. Okay, so we've made this operation and created this data, but we have not written the data to the file yet. It's sitting in memory. So if we E out of the plot routine, there's a pending operation. It's called the soft exit from the current subroutine, and then the data will be written. If we don't like the results, we can X and terminate any pending operations and go back to the beginning. So we want to E, the data are written, and now we'll see the band passes. Now let's go back to T for transferring copies, and we want to copy that. So now we have a complete set of spectra. We have our ASD wavelengths, bandpasses, and our forced right spectrum, ocean optics wavelengths, bandpasses, and forced right spectrum. We don't have the correct wavelength pointers, but there's two ways to do this. When we did the copy, we could have branched into the information change routines and changed it. And it's a little tedious. It's much easier to use one of the independent programs. So there's SP set wave, and we're going to set the wavelength pointers and band passes for SP-temp-U, and we'll start with the band passes here. Record 33, we're going to change that to 0.2, 27, and 33. Okay, and it'll tell us, let me expand our window here a little bit. It gives us the current and new. Type yes, return. If you're confident in the results, so we're going to now change 39 to be the same two. We know those are right. We can say force, and it just does it. Now when we print it, we see 27 and 33 are done. Okay, now let's do the band passes here. So that's correct. So that's got the right wavelength pointer because we created it. When we created it down here, the wavelength pointer was already set. So we just need to set it on 57. So record 57 needs to have the wavelength set to 45 and the band passes to 51, and we can do force. Okay, now we see 45 and 51. So we're good to go. Now, what we need to do is figure out if the spectra are, how they overlap, if they need any adjustments, and where our splice point would be. So the easiest way to do that, let me do OV1, which is red. So we'll do that as the long wavelength data set, the ASD. So U39, U27, then OV2, which is blue, we'll do for the UV, U57, U45. And I like to start a log of what I'm doing with notes for the operations that I'm going to do and the calculations that might be needed. So I'm going to do notes dot. So we can put these in there. So if we wanted to overlay these again, we could. And these are not saved in the restart file, so you'll have to load them every time you start Specpr. So now and then the other things that we need are, we need this group here. So let's put that up here. And to be sure what file this is coming from, I normally put that in there too. So now we have a good record of what we're doing. So to plot these, let's choose the U39, and since the wavelength pointer is set, we can say ampersand. So the black is the ASD spectrum. The blue is the overlaid ocean optic spectrum. We don't see the red because the black is the same as the red, and black is plotting on top of red. So this is our overlap region. Let's expand that. The overlay is close, but not necessarily exact. Shift S works well in this case. So let's go from about there to about there. Now we see that the ocean optics data is noisy in this region, but it does have higher resolution, although I don't see any sharp features. The olivine has structure in here that is seen by the ASD spectrometer. One of the problems with different spectrometers is as you go to their extremes of their ranges, signals tend to be low, and there could be scattered light in the instrument. And with the ASD spectrometer, using a tungsten lamp, we know the signals are low at the short wavelength end, and usually or often there's an upturn, and you'll see that spectra from the ASD and a UV instrument that covers the range with a higher signal and a different lamp, like a deuterium lamp, will diverge here with the ASD spectrum going up. This one's not too bad. If we did the same test with a hematite spectrum, which is high red reflectance and low UV reflectance, that combined with the tungsten lamp black body means signal is very low over here, and a tiny amount of scattered light will change, and we'll see the spectra diverge more into the UV, including full upturns, much more so than just a couple of channels here. But this spectrum looks good. So now scientifically which point to choose, and that's a strategy left up to the spectroscopist, because there is no one single good answer. For example, you could choose this region where they match better. We could scale the UV spectrum up and choose the high point here. But I want to keep the structure in the scene here. It'd be nice if the ocean optics data were higher signal to noise. So the question then is where to do the match, and there's an odd feature in the ocean optics data here. That's probably an artifact due to switching over from the spectrum was taken using two different lamps, and I believe the switchover point is in this region. So I would think I would choose something here. So let's zoom in on that a little more. Not exactly sure where. If we chose something like this wavelength in here, let's zoom in just a little bit more. So now to get a little more precise on what we're doing, I kind of like maybe splicing about here. So this, let's do the Shift G, does a graphics cursor readout, and that wavelength is 3.7889. Okay, I right-clicked, got out of that mode. Wavelength marker 1 equals 0.37889. So the next step is we're going to have to multiply the ocean optic spectrum to be higher up to match here so we can splice it nicely. Let me copy this so I have a record of it. One thing to note, one wavelength marker can have up to 5 wavelengths, so we put the color first so we can list all 5 if we need them. But when you enter it, the red should be a comment. So if we cut and paste that, it works. If we just grab this line and pasted it here and then pasted it into Specpr later, the red would be confused. Okay, so now the question is reading out. So we go back to the graphics cursor read, and if we do this point here, we see this has a value. It has a value of 0.59943. Ocean optics. That would be down here. Now we can get out of this and go load the ocean optic spectrum and read the value exactly, or since we're zoomed in pretty well and well within the noise of the data, we can just select that point, and the ocean optics, the cursor position is the upper line, and that is 0.58829, 0.58229, 0.58229. ocean optics times. There's a handy calculator in Linux, BC arbitrary precision calculator. If you include a -L, it includes some math functions. We don't need those at the moment, but you can get sines and cosines and things like that. So we're going to just ratio these two. So our scale factor is 1.0. Oops, we don't need all the precision. So that's more than enough precision. So let's right-click, get out of the graphics cursor read. Then we exit here. We're just in a plot. Exit, go to math. So we want to multiply U57 times the constant 1.024, 1.02944, and we want to be sure we have the right wavelengths because we're not using the right ones at the moment. So that would be U45. Okay, we're using the right number of channels. We have that. That looks good. We want to write to U, and this is there's round off error in the floating point number that gets decoded, but that's, you know, within a part per 10 million, so that's fine. So this is what we now have in terms of the ocean optics data is the black, the red is the ASD, the overlap through this region is fine. So I will continue to go with this point. So the question now is the splice point. We're going to use channels 1 through, need the shift G. Uh, 542, that's right up here. Okay, so to get the ASD wavelengths, we need to remember we've done a math operation. This looks good. We're going to accept it. Right-click to get out of the graphics cursor read. Exit the plot, and the data is written. Then let's go to the display routines and bring up the ASD spectrum and get our graphics cursor read. And we want, since we're including this point from the ocean optics, let's choose this point as the next point. So that'd be channel 40. So 40 to 2151. So total is, so there's 542. And for this one, we're going to have 2151 minus 39. So we're going to have 212 plus 542. So the output will have 2654 channels. So okay, now we have all the information we need. So here's our adjusted spectrum. So we'll need to splice 3 sets: the wavelengths, the bandpasses, and then the spectrum. If we have a bunch of spectra to splice together, it would be nice if it worked out to use the um, same wavelengths as a splice point. Then you only need to do the wavelengths and bandpasses once. If you vary it for each spectrum, then you've got to splice the wavelengths for each and the bandpasses for each, and it just gets more to manage. Um, Scientifically, that may be the best thing to do, depending on the idiosyncrasies of the spectrometers to get the absolute optimum combined spectrum. Okay, so right click, get out of graphics read. Now we need to go back to math. And we need to do the splicing. If you don't know which function to use, you can look through F1 and find them. It's not called splice, it's called merge. I would rename this. We need aliases for function. So we have one alias, we need a second alias. Anyway, it's function 13 or merge. So the first spectrum to splice is this one. And our problem is we may need to create this first before we continue on. So U51 merge, and I have to spell it right. And we need 2654 channels, so we can try this. I don't know if it works with this function, but we'll see. Yeah, see, it's limited to no more. So we need to create a dummy wavelength set. So we'll do that with a line segment generator. Or we could, there's another way to do that. Let's go back to T and go to, and just do V57 and just set the wavelengths as channel number of 2654. If we so I'm changing the mode to channels down here, and this will show us just channel number. Okay. So if we plotted, for example, V39 or U39, this is just as channel number. And there's 2151, so it ends over here, not the upper limit. But this is fine. We got the right number of channels now. So let's go to math, and we're going to do, so we're 51 is the wavelength, so we're going to do the wavelengths first. And we're operating on 2654 channels. So the second wavelength set will be the ASD spectra, and that's 27. So U27. Technically, wavelengths are supposed to be capital U 27, but the data here are just create as an array, so it doesn't matter. So we'll just do U27. So A is the UV, so A 1 through 542, and B is the ASD channels. And now let's save this. Then we can cut and paste it with each splice that we do. We're going to write the results to U, and remember the this says bandpasses, so I chose the wrong one. Right there is a red flag. I chose 51 and I should have chosen 45. So here's where we X out and we try U. And one advantage of this, if it of Specpr and how it tracks things, is there's a full history of all the operations. So if you got a funny result and you didn't notice it and you went down the road, you can back up through all the Specpr files and look at the histories and see where your mistake was made and then correct it from there. So we're going to do U45, F13, or merge. Then that's fine. Then the wavelengths for the ASD is U27. And now we can just cut and paste this right to U. Now we see the preserve the title. It says wavelengths. Before it said bandpasses, so that was a red flag to me. And up here it says wavelengths. So we want wavelengths, and this is 0.2 to 2.5. You'll notice when I'm doing these, I write things down and then I cut and paste, or rather than typing in 45, I'll cut and paste that. That way I do less typing mistakes. So here's the merged wavelengths. Let's change the vertical scale 0 to 2.6. And now we can see, so this is the wavelengths for the ocean optics and the wavelengths for the ASD. And remember, our breakpoint was 542, and that's about what we're seeing right here. So this looks good. We can write that. Type E, it gets written. Oops. So now we have the new wavelength set created. Okay, now we need to do the same thing with the bandpasses. U51. But now we actually have wavelengths, so it would be better to do this, but then set our wavelengths. So then the wavelength pointers will get set. We can also do this later in the plot, but we can do it here. So we got the 2654 channels. So U51, the bandpasses, the bandpasses for the ASD is 33. Got to press return. U33. Cut and paste our splice. Right to U. And this is bandpasses. And we can just copy. And these are going to be down low. So so there's our bandpasses. Okay. That looks good. And we see that the wavelengths are now 69, so the wavelength pointer will get set. And now we see the wavelengths. Now the date did not get set because this was, the bandpasses were artificial, so there was no actual origin, although we could set the origin to today when the data were acquired. Okay, now we do the spectrum. So the ocean optics spectrum that was scaled is U63. The ASD spectrum is U39. Do the splice, write to the same file, and then this is forced write, absref, I don't think this fits. Maybe 2654, or we could do, yeah, 2654 channels. Then we know it's something special. You can also, if you know the range of your data, right now the range of the plot is 0 to 0.02. You can change it here, 0 to 1. And we're still in channel mode, but we can change that to, notice it's the second letter of each of these. So for wavelengths, it's A. And let's change the range, 0.18. It's actually 0.18 to 2.5. Now the data down here is also a case where it's probably spurious, so the good data is probably out to there. Now we have two choices. Actually, we also need to turn off the overlays. OV redraw. So we could accept that as is, and in some cases that might be the best thing to do, because that's all the data, and then you can make a second, and let's do it this way. So there's some spurious data out here and some spurious data here. That this is implausible for this to be real, so I suspect that it's wrong, and it's the end of the spectrometer where the signal's low. So let's chop off the data here and chop off the data there. Now, Specpr, one way to do that would be to decimate the wavelengths and have a reduced wavelength set that only covers from here out to, just before 2.5. But every spectrum will have different idiosyncrasies, and the data that you need to reject may be at different wavelengths. Some data may be good all the way out here. Some data may be good to a shorter wavelength, and it may be important for some interpretation of, say, some spacecraft data. So Specpr tracks deleted points. So let's go ahead and save this spectrum. So we have this merge is pending, and we type E to exit. The data is written, and we can check our range here. So now let's delete the bad points. So let's get out of this, go to T, and we're going to do something different here. So we have U85, and notice while our wavelengths are, our pointer is correct, that bandpass pointer is not. So let's fix that. We can do that with SP set wave. We're going to change U. This is one thing nice about Linux is we have an open file here, but we can modify it with another process. So we want 69 is correct. Yes, 69 is correct. And the band passes are 77, and we can force this. Okay, so now 69 and 77, all while Specpr has the file open. Okay, so we're here, and we're going to copy the file to the same, copy the record, copy this spectrum to a new record. So we would do that with that, but we want to go into the, C was actually originally for CRTs because everybody was on CRTs. So go to the CRT plot routines and then copy to U. So now we're in the plot. Now we can zoom in. And the question is where to delete. The data up through here are certainly implausible. So I would probably go through and delete up to this channel, so 76. So remove 1276, and then C. So those are deleted. Now in the file, it's marked as a special value. The special deleted point value is minus 1.23 times 10 to the 34. It's an implausible number. And when you do any math, all the deleted points are tracked. Okay, now let's go to the other range, 2.3 to 2.52, auto scale. Okay, so now let's Shift G, get our graphics cursor. That point looks good. That point is plausible. This is not a plausible absorption band, so I'm going to delete this channel here. So 2634. Remove 26. Wait a minute. Oh yeah, 2634 to the full range is 2654. And then if you press return, you can enter more deletions, or type C. We could have put the C on the previous line. So now that's gone. So now the spectrum looks clean. Change our scale 0.18 to 2.55, 0 to 1, and that's our final spectrum. Looks beautiful. We can then put that into a spectral library with appropriate documentation. We haven't changed the title though. So what I would tend to do, and we haven't written it yet, so you can go to information change, and we can change the title. And I just do something like edit 1. And then we're good to go. We can page through and look at other information to see if we want to change anything. Here's the date when the data were last processed and time. The data were obtained in 2019. All of this looks good. Our pointers, the temperature, it was room temperature spectrum, so we'd have to, if we wanted to fully document this, we'd put in the angles of emission and incidence and the phase angle, and that would then go into could go into a spectral library. Okay, so if we E, it gets written, and there's our final spectrum. So it looks good. We're done. Thank you for listening.